Okay, thank you for staying here for the last presentation of the week. And for this last presentation, I don't wanted to talk only about elastic anisotropy within crystal plasticity. So I decided to change the topic to give you a more global view about my PhD subject. And so... Ah ouais. Ah. And so I will talk about the full field modeling of the microstructural evolutions of mantle rocks. So why do we want to understand the microstructural evolutions of mantle rocks? The first reason is that the lithospheric mantle controls at the first order the lithosphere rheology, and so the tectonic plates mechanics. Here, here it's a numerical experiment where the author have done a lithospheric model with 3 layers, an upper crust, lower crust, and lithospheric mantle, and they place some weak scars, weak rheological scars, represented by those lines in the model. And after the deformation of the model, you can see that the main deformation is located at the place where the mantle lithospheric scars were. So this illustrates that the part of the lithospheric mantle controls the mechanical behavior at the first order of the lithosphere. And as for metals, the microstructure rock features are strongly related to the mechanical properties of the rock. The first important characteristic of microstructures is the grain size. The deformation regime of the rock can be strongly impacted by the grain size. Here you can see that in the diffusion creep regime, the strain rate represented by those lines here is strongly impacted by the grain size. When you decrease grain size, you strongly increase the strain rate. Another feature which is very important is the texture of the rock. As the mantle rocks have a strong anisotrope plastic behavior, when you have a zone which is strongly textured, it can induce a weaken in the rheological properties of this zone. The second point, which is interesting to study the microstructural evolution in rocks, is that the microstructure contains a lot of information about the history of the rock and about its thermomechanical history in particular. For example, true geologists, not me, but true geologists can, by seeing this kind of microstructure, can say, yes, this rock has been deformed in this sense of the shear with this intensity. With this microstructure, we can see that the grains are large and the triple junctions are in 120 degrees, and we can say, yes, this rock has not been deformed and since a long time. And so all of these reasons are good reasons to study microstructural evolutions of mantle rocks and rocks in general. Okay, now I will try to convince you that numerical experiments can be very useful in geoscience to help to extrapolate laboratory experiments. Mainly because the mince. because the laboratory experiments in terms of strain rate and in terms of stress are very far away from the geological conditions. This is for deformation experiments, and this is more for grain growth experiments. You can here are the time scale involved in nature and the grain sizes that we can met, and the laboratory scope is very small within this graph. I will try to convince you more with this. Here I plot the grain growth kinetics for pure olivine, calculated using the classic mean field model we use for olivine, and which is calibrated by laboratory experiments, which represent like points in this curve. And if we extrapolate the laboratory results, you see that the grain size increase until values that we never met in nature. And more, the time scale here are ridiculous compared to the time scale in nature. Here, there is a lack within laboratory experiments, because if a mechanism took place and is important, I don't know, near 5 millimeter of grain size, we can't detect it within laboratory experiments, because if you want to observe grain size differences at this grain size, you have to do annealing experiments of 50 years or 100 years, and no experimentalists want to do this kind of experiment. So for this, numerical experiments are maybe very useful to link laboratory experiments and nature observation. It could be used as an extrapolation tool. Okay, so now I will present you the numerical framework I use. I use the level set framework that we have already talked a lot this week, so I don't will explain the mathematics. The code I use is developed by the team of Marc Bernacki at CMF. And this numerical framework is really convenient because it permits to model a lot of phenomena as grain growth, inner pinning, diurics, and we can also add crystal plasticity computation. And my goal is to adapt, to use and adapt this numerical framework for thermomechanical conditions and material which are more relevant to a geological context, and in particular related to the lithosphere, to the upper mantle scale. So now I will present you the main results I've got during my thesis. First, I wanted to be able to reproduce the grain growth kinetics of pure olivine, which is a major mineral constituent of mantle rocks. And so for this, I use a methodology presented by Baptiste at the middle of the week. I calibrate my grain boundary mobility on experimental results of annealing experiments for pure olivine. And then I try to estimate the time needed to erase a fine grain band, which we call ultramilonite, if the rock is only composed by olivine. So if we do this kind of model and we run it at a lithospheric temperature, we see that this ultramilonite band is completely erased within less than 1 year. And this is obviously completely unrealistic compared to the geological timescale. So after that, we wanted to include the effect of the second phases on our model, because there are a lot of second phases within rocks in general. In the mantle rocks, you find obviously olivine, which is a major constituent. You can find pyroxenes and spinels. And generally, the presence of second phases has the effect to impede the grain boundary migration and so to reduce the grain growth kinetics. Here you have two made images of peridotate from a French Massif Central. Here it's olivine grain boundary, which is pinned by spinel particles. This can be modeled through the Zener pinning mechanism if we consider that the spinel particles are static. And we do this because the Smith-Zener pinning was already been implemented within the level set framework. And within this image, the lighter phase is pyroxenes and the darker is olivine. And the pyroxene grains also growing simultaneously with the olivine. And but it impedes also the grain growth. You can see some phase boundaries which are curved near triple junctions involving phase boundary, and this shows that the presence of this second phase is impeding the grain growth. So we try to take into account in our model this dynamic second phase which is evolving simultaneously, and for this we use the numerical development of Julien Petit, which allows to account for heterogeneous grain boundary characteristic, and we attribute different surface energy and grain boundary mobility depending on the type of grain boundary. For olivine grain boundary, pyroxene grain boundary, and olivine pyroxene grain boundary. And by calibrating our phase boundary mobility onto experimental annealing of a mixture of pyroxene plus olivine, we are able to model the grain growth kinetics of this mixture. We also calibrate a mean field model which accounts for the presence of static second phase as Pinel, accounting for the grain size of the static particles and the volume fraction. We also account for the presence of dynamic second phase as pyroxene, depending on their grain size and their volume fraction. And now we are back to natural object, and these are three microstructures provided by Andrea Tomasi. Here it's deformed, they are xenolite, and this is more deformed than this one. And what we did with those microstructures, we immerged them within our level set framework, and we simulate their grain growth. And then we plotted our mean field model, and we try to place the three grain growth kinetics within this curve. And if we trust this model, we can say that this rock, this microstructure, has not been deformed since 200 kilo year compared to this one. But this is still too short compared to the normal time for this evolution. So at this time, I think we have learned something, because what we did with this numerical experiment is we used laboratory experiments, and we put in our model the mechanism we understand from the laboratory experiment, and we did a kind of extrapolation through our numerical experiments. And if now with this clean extrapolation we obtained too short time, this means that we are missing something within laboratory experiments and numerical framework. We are missing a mechanism, and this is an information. All right. Now I will talk to you a little about plastic deformation, because my goal is also to model the olivine dynamic recrystallization, and so I have to model plastic deformation of olivine. And for this, I use crystal plasticity. And the first thing we have to define is a list of slip system. But here it is a problem because if we only account for the slip system, we observe within olivine the flow surface is not closed. Here you have two cuts within the flow surface calculated with those lists of slip systems, and you can see that for some stress directions, the crystal cannot deform plastically. And so this causes numerical problem, numerical issues, because if we deform the finite element mesh, and if some elements are bad oriented with respect to the stress, they can only deform elastically. And if another element is aside of this element and deform plastically, you have very huge stress gradients. And so the finite element resolution is very difficult. And so for the moment, I cannot deform my models more than 15% of microscopic strain. But we can still study the plastic deformation of olivine until 10% of macroscopic strain. So for the rest of, for the crystal plasticity, I use classic power law flow rule. I use also Taylor relationship for the hardening, and for the dislocation density evolution, I use Yoshi-Lasraoui-Jonas type law. And so the only two parameters I have to calibrate are the hardening and recovery parameter. I used to calibrate them. I use monocrystal compression experiments at 2 temperatures and for 3 different orientations of the crystal with respect to the principal stress. And this is the best fit I can obtain. And after that, we ask ourselves if the anisotropic elasticity have an influence on the subsequent plastic deformation, because as you can see in the elastic constants here, the olivine is quite anisotrope. And so we implemented several features in our crystal plasticity code and in our finite element resolution to account for the elastic anisotropy. And then we test for a polycrystal model if there are some differences. So we began with a quite random texture, and after 7% of macroscopic strain, we can see that there is little differences between the local dislocation density. There is very small differences between lattice between texture. If we begin with a strongly textured polycrystal, this is the same. We have very small differences between local dislocation density and textures. If we have a look on the macroscopic mechanical behavior, you can see that there is not strong difference. The dashed line are the anisotropic ones, and the full line are isotropic. The dots are the data of Julien Gasque that Sylvie presented at the beginning of the week. And we can see we are in good accordance with this data, but it's strange because in those experiments, there are not just the plasticity which is activated. So, okay. And now if we have a look on pressure along a line connecting the two opposite edges of the simulation domain, we can see that there is not strong differences between between the pressure. So at this point, we can argue that the elastic anisotropy does not have a strong impact on the plastic deformation. Okay. For the end of my thesis, I want to have a dynamic recrystallization simulation of at least olivine, and so for this I have to deform more my models, and so I think I have to implement a kind of isotrope mechanism which will accommodate strain instead of the elasticity, because if not, it doesn't work. What I want to do and what I begin is to take into account the solute drag effect for the grain growth, because we see there are a segregation of impurities at grain boundaries within olivine, and the level set formalism could be modified to take into account the pressure induced by the segregation of these impurities. And with this, I am hopeful for adding 2 zeros within this graph. I am hopeful. And all right, and thank you for your attention. And if you have some question, ideas, proposition of things to do, or postdoc or thing like that, no problem.